Thank you. This is very nice. Okay, so there'll be, hopefully my talk will be organized in 3 parts. First, I will review something from what I said. I'm sure everyone remembers. Next, I will talk about light ratings. Things like technology. And then finally, I will talk about format. Okay, so let's start with some review. So start with an integer k. What I want to do is define the symplectic manifold, and from this symplectic manifold, we'll later be able to produce the topology. So the first symplectic manifold we should study is called the K nullifier. In dimension 2. The way this is defined is that you basically just take the locus x surface y squared plus p of z equals 0 inside of C3, where p, let's say, is a generic polynomial of degree, and hopefully I wrote something that I always get this wrong, and it's probably wrong still, okay, it's 1. But I'll do some examples that will allow us to check whether I got it right. So this is just some surfaces here. If you treat this generically, you get something smooth. And somehow standard fact that once you're in that sort of situation, you're defining some great variety by simplifying equation. If you deform the equation a little bit, of course you have great variety changes, so you're doing algebraic geometry. But if you're doing symplectic geometry, it doesn't change. So as Ivan said, you want to consider some sort of space of all possible polynomials. That's the configuration space, which is an interesting fundamental group. So all the symplectic manifolds you get are symplectomorphic, and moreover, if you make a loop in that configuration space, you get symplectomorphism. So the way I think about this is that we take what we call the standard optimization, which is the z coordinate, onto C. So notice that if I take this map, the fibers of this map are, well, x squared plus y squared equals 0 if z is a root of p. Okay, so x squared plus y squared equals 0, that looks like this. It's 2 branches, x equals plus or minus I times y. On the other hand, if z is non-zero, what you get is, well, something that, what you get is a conic. Okay. If you try to solve the equation of surface y squared equals epsilon, you just see cylinder is smooth as if p of z is not zero, and p of z is not zero. So what that means is that the way you visualize this is that you have, as I said, a vibration over the disk. There are some critical points. Really doesn't matter where they are, so let's just assume they're on the r-axis. So fibers over here are cylinders, and fibers over here. What happens is that you took the central circle in each cylinder and you relaxed it to a point. So just yes.
You might think I'm stupid, but why don't you have in this federation a connected component of the fiber for each per image of yeah.
I don't think you're stupid, but I still haven't understood the question, but I'll just move on. Okay, so the examples to keep in mind are k equals 0. So this is supposed to be the A0 multiplier, and I claim that that's basically a copy of C2. And the reason is that if you write down x squared plus y squared plus z equals 0, okay? So basically that means you choose any x and any y, and you can always, there's a unique z that solves this equation. So this is just the C2. You can imagine it's just this is the graph of a function over C2. But this projection, you see, if you parameterize this by x and y, this projection is xy goes to x over y squared. Okay? So z is. And in this situation, you get exactly one critical point, and this is what is called standard Lefschetz fibration. The next case to keep in mind is if you k equals 1, then you're solving x squared plus y squared plus z squared equals. No, that's bad. So remember, I have to choose a generic thing, so let's just choose it in something like this, just to be concrete. So in that case, there are two critical points at plus or minus 1, corresponding to these two roots. And this, people will tell you, is basically symplectomorphic to T star S2. Now in T star S2, there is the zero section. So we should be able to see the zero section from this picture. And the way to see it is by the theory of matching cycles. So what you do is you go back here to this very general picture and you say, well, the smooth fiber is a cylinder. The singular fiber is this two lines like this. So if I take the cylinder and I try to move it by some sort of parallel transport towards that point, towards that singular fiber, what happens is that the circle collapses. And it turns out that it's the same circle that collapses whether I go here or whether I go here. So that means that in the smooth fiber over this, I have a circle, and I can parallel transport the circle, so at every point here I have an S1, but that S1 collapses to a point, so I get a picture like this. Okay, and that's a copy of S2. Now, the first time you encounter this, one is very concerned about whether this copy of S2 is actually smooth or not, because the circles will collapse. And the way to do this is you think about what's happening in C2, and you realize that there's basically fibering over this arc. There's arc plus r squared inside c squared. Take r squared inside c squared, it projects down to this arc under this map, x squared plus y squared, and it exactly gives you the local model near these singularities. Then you glue the local model from here with the local model from here. There's basically a unique way to do it. So you get a Lagrangian stream. Great, and we have one Lagrangian stream. And the higher guys are basically the same, and there's if you choose an arc between two of the critical points, you can construct a Lagrangian. Okay, so what do I want to do with this? So from now on, K is odd, and it will be 2 at minus 1. Then probably I made a mistake again, but it's okay. And moreover, in all my pictures, we just assume critical points on the real axis. So this construction of matching cycles means the following: that if you have any crossless matching in C, so what does that mean? That means you connect, actually I'm just saying the upper half plane since that's what I will be doing. So you have your, let's say there's 4 of them, you connect the critical points of this map, which means it's finite set inside this real axis. You connect them by arcs. The arcs are in the upper half plane, the arcs won't intersect each other. Okay? If you have a crossless matching, then what you get is a collection of Lagrangian S2s inside this A2 minus 1. That's the collection of n Lagrangian S2s. With the special property that, well, first of all, they don't intersect each other. But something stronger is true, which is that the projections to C do not intersect each other. Whose intersections, whose projections C do not intersect. Okay? Now, if you have such a Lagrangian, or such a collection of Lagrangians, you take the product. So the product lives inside the product of this guy, but that's just from diagonal, so you can take the quotient by the symmetric group. remember the information of this vibration, and moreover, we will remember the information of these projections on this joint. This is a doping substance. Okay. So, what properties does this YN have? Well, what we've just seen is that crossingless matchings produce Lagrangians inside this YN. So the notation will be C is a crossingless matching. I have something called LC. The topology of this LC is always S2 to the N. The other thing I can do is that since the array group acts by symplectomorphism on this space, which is -1. It also acts on the product, and then on the symmetric product, and then on the resolution of the symmetric product. And moreover, the way it acts by symplectomorphisms is compatible with this vibration, so it acts by symplectomorphism on the relative public scheme. Also acts on YN. So these two pieces of information are what you need in order to define symplectic quantum homology. You just define some group, let's call it SKH, of one crossingless matching, a braid, C, and another crossingless matching, to be the Floer homology of the Lagrangian associated with C with the image of the Lagrangian associated with the first one with the image of the Lagrangian associated with the second one under phi, where here I'm not writing any, I'm just writing phi for both for the braid group element and for its action by symplectomorphism. So that's analogous to one of the definitions of Floer homology that I introduced last time. In fact, we also more or less wrote down this one. They are a lot of pieces of chalk. Okay. Okay. So the first. So this is what side is. Although not in this language. Although not in this, they work, as I said, they work in the Milton slice instead of this relative Hilbert scheme and Chicory, and nonetheless we showed those two spaces on this. Okay. So the conjecture, the idea is that this group here that we have is some simply braided version of Floer homology. So one of the first questions you might ask is, what about the vibrator? What about the second braid? So that's the second part of this. Before I go further, I just want to make sure that not everyone's asked. This was just, my goal was just review in 15 minutes what I said this. Okay, so I want to explain some symplectic construction. Yes?
So the C plus and C minus here, are they particular? Are they the special crossingless matchings that I've been said that?
No, you take any crossingless matching. So, okay, let me pause there for a second. So so my point of view is like this. I start with a crossingless matching, let me draw one here. Okay? Then I take a braid. Whatever. And braid. Then I take, so this is C plus, this is phi. That's a very complicated thing having that. And then I take another crossingless matching, which is basically any crossingless matching. Something like that. Okay? That's C minus. And that will give you a knot, just as a link in full generality, as a closure. And I don't really assume that it's of the special type that I need to turn out. Okay.
Is that good?
No, it's fine. I just was not what I expected. So of course there is something something that I'm not even explaining because I wrote down this level group and I said, well, okay, this is Z-graded. Because there's a lot of choices that go into making sure, there's a lot of input that goes into making sure that thermology is actually Z-graded. I just will say nothing about that. I'll just move on to the next step of trying to construct this. So, the idea for constructing the second gradient is actually very general construction. So this is an adaptation. So what we will do is some sort of adaptation of work of Simon and Solomon. So they phrased everything in terms of symplectic homology. So they phrased everything in terms of symplectic homology, but symplectic homology is very hard to compute. And so instead of defining things using symplectic homology, we will define something which relies on the geometry of these spaces. Okay? So we won't be doing symplectic homology directly, but there should be a way out there for translating everything that we're about to do into precise language. So what do I want to have? Let's consider the following very general situation. So X is some symplectic manifold. So now we'll not worry at all about technicalities. Symplectic manifold is supposed to be well behaved some way in infinity, let's just not worry about that. And I want to assume that you can add the divisor to X. So D, so this is another symplectic manifold, but basically I want to make sure that you can write X is equal to X bar minus D for X bar is equal to this. This is again another symplectic manifold. The simple situation is to assume that X bar is a compactification of X, but that's not exactly what I want to assume here. I just want to assume that it's a partial compactification. So out of this geometric data, and later on I will tell you exactly what X and B are in the situation. Out of this geometric data, I want to produce a bigrading. I want to produce bigrading on this chi-category of X. And this is key. I'm not going to be computing anything with this chi-category of X bar. There will always be this interior, this X bar. But I will use the compactification to produce some extra structure on this. So, again, the toy case will be X is equal to a 2n plus 1. And then I have to tell you what is this partial compactification of a 2n plus 1 that you should be considering. And it's a fairly obvious one to write down. What I want to do is I want to preserve the fact that I have vibration over C. Okay? And so if I want partial compactification, basically the only thing I can do is I can try to partially compactify the fibers. But the fibers are extremely easy to partially compactify. They're just cylinders. You add a point of plus infinity and a point of minus infinity. So so X is this, and then X bar, so this H here plus 1 bar is obtained by adding two sections to the vibration. Okay, so now what used to be, so for example, for T star is 2, I get a vibration with fiber over generic form point P1, and fiber over a singular point. Well, there used to be two planes meeting at one point, and now you have two copies of P1 meeting at one point. Okay? And what you can see basically is that, just for expert, this has term number 2, and this has term, each one of these is term number 1. So you can construct this space explicitly using this geometry, but this is really how you should think about it. Okay, now I'll go back to the very general situation. So I have this divisor, and what I'm going to do is I'm going to count the morphic curves that pass through this divisor exactly once. But I won't be counting them in the usual way. I'll be counting them in some relatively strange way. So to set up, we first choose a perturbation. Let's call it d epsilon of d inside epsilon. So here's d, here's the space, and then you just choose some perturbation. Notice in this situation it's very easy to choose a perturbation so that it doesn't intersect d at all. So they're completely distinct from each other with this special case. And now, for any element, any object, let's just say any Lagrangian in X, we want to define an element of the Floer homology. How do we want to define this element?
So this part of the question is not getting any points from the syllabus. It's kind of.
No, it's not. It's some, so in fact, I only partially quantified the things of which I was taking the differences.
Right. And then now you're taking the listing of this and I'm taking what we said inside that.
Yes, later that's what I will do. Okay. So we want to define an element of the Floer homology group of any Lagrangian. So how would we do this? Well, we do this as usual by drawing pictures. So the picture you want to draw is the following. So let's call this element something. Let me just call it delta. Delta 0. So you're going to count disks. The disks are going to have the Lagrangian boundary condition on L. Okay? There's going to be one mark point that we're going to evaluate. So you call that delta 0. Okay? The disk is going to be, so if you, let's set it up so that at the origin it passes through D. Notice this disk now has no automorphisms on it. But what I want to do is I want to consider the line that goes, the ray that goes from the origin to this point here, to 1. I guess it's minus I in the picture. And I want to count disks which intersect the epsilon at an arbitrary point. So another way to say this is, there's a one-dimensional family of disks with 2 mark points in the interior and 1 mark point at the boundary. Okay? And over this one-dimensional family, I want to count rigid elements, exceptional solutions, whatever you want to count things such that when you allow this point to vary, you have only a virtual dimension, not 0. So the claim is, so that if certain Romanov invariant of X bar vanishes, or a certain vanishes, then and Floer homology of L is all point. Then we actually obtain the delta 0 in the Floer homology. Okay? That's one way of that's a statement. So just so that it's clear, why I'm saying this comment by the Romanov invariance is that these are disks in X bar. Okay? Even if you assume, as we started before, that X has no closed homomorphic curves, because X basically in our situation is always exact symmetric manifold, is trivial manifold, X bar already has these spheres in it. So you want to make sure that these spheres are not going to interfere with you. And it turns out actually in this situation that this Romanov invariant is related to Chern-1 spheres. So if you look at this example, you kind of get worried until you realize that there's 2 of them. and they end up canceling. So, yes?
Is it really necessary to reduce the complexification, or could you use some orbits and infinity?
You can, as I said, if you were confident about your ability to compute symplectic cohomology, you should be able to just write down an element of symplectic cohomology and thus.
Right, so this is just a sort of technical.
This is a way of kind of producing it without going into symplectic cohomology. It's particularly important here because then we're going to pass it ahead. And then I would have, I have no ability in computing this symplectic cohomology. That's why I've tried many times. So that's indeed the case. But the most important thing is that you don't want to, you really have to let this point vary along. Okay? So it turns out that this element is in HF upper 1. And now we have a definition, which, as I said, this is the point. This is the adaptation of the work of Seidel and Solomon. So L is, okay, so I'm going to write down a word, and I really should write infinitesimally equivariant. Actually, let me just say infinitesimally invariant. That's more meaningful. That's correct. If delta 0 vanishes. Okay. So the origin of this terminology of being infinitesimally invariant comes from mirror symmetry. So their work is trying to understand the mirror of the existence of a C-star action on a variety, and it turns out that the C-star action is the existence of certain cohomology classes, and this is some condition on the Lagrangians that is mirrored to certain property of coherent shapes with respect to C-star actions, and so that's the word we're stuck with, even though it looks like it's completely unmotivated in this situation. Okay, so once you have this, what you can do is that given any pair L0, L1 of infinitesimally invariant Lagrangians, we will define a relative bigrading slur cohomology of L0. So the first one of these gradings is the one that I was about to say everyone is familiar with, but at least the literature is familiar with. It's just the homological grading on Lagrangian homology when the instructions vanish. So I will call that the homological grading. And I will say nothing more about it. First is the homological. The second is obtained by counting some pictures that are very much like those above. So what you do, the second gradient, which I will call weight, you now consider, now you have two Lagrangians, so define as follows. So you take two Lagrangians, and what I will do is I will first define an endomorphism defined by obtaining an endomorphism delta 1 of slur homology of L0 and L1. So how is delta 1 defined? So I look, yes?
It's delta 0. Coming from Childson is just the image of the class in symplectic cohomology to under the manifold symplectic cohomology to HF star data.
No.
It's not that.
It is not. Well, I mean, which symplectic cohomology class? You can produce some symplectic cohomology class of this property, yes.
Their construction starts with the class in symplectic cohomology.
Yes, their class is. Yes, it is. But it's not.
It's the image of that.
It is the image of that.
Yeah.
Yes, but it's not the naive one you have constructed from the device.
Yes.
It differs from that by far. Okay, so now we draw pictures where here is R0, here is R1. Those are my Lagrangian conditions. I still put my D over here. I still put my D epsilon you have an input, which is, let's say, x, and this is what you call delta 1 of x. Before we had no inputs, we just had an output, so we had an element of the simpler analogy. Now we're about to put in something, make it interact with this divisor and this with the epsilon in the interior in a prescribed way, and then we have our output. So that defines, and then the morphism of this lyrical homology, and then you can decompose HF star L0 L1 by the generalized eigenvalues of type 1. So, of course, in order to have generalized eigenvalues, you may want to. So that means that it's graded by the algebraic closure of the field that you started with. Okay? So the grading, i.e., if you start, you work over C, work over Q, for example, you obtain grading by the algebraic closure of the Q. Second grading, the weight grading. And this is called Q bar. So first comment is that why did I say relative? Okay, it turns out that if you try to think through the whole construction, this element, as I've been trying to explain it, is not well defined because there could be some bubbling, but that bubbling is taken care of by the fact that something vanishes cohomologically at delta 0 is equal to 0. But then you actually have to choose a chain that kills delta 0. Okay, and that choice of chain is why you only get a relative by grading, but you can obtain an absolute by grading by making some choices that we completely understand. So you can obtain an absolute by grading by making choices which are parametrized. The choices on, let's say, the original Lagrangian L, which are parametrized by H0 of L for some H0 of L. And there's some choice having to do with the first grading, some choice having to do with the second grading. Of course, if L is connected, basically there's a Z choice. But we know exactly what these choices are. The second thing to say is that in practice, this is often, this by grading is often by grading by the integers. Second grading is integral. And that's what happens in our situation. Okay, so now let me say a few words about what this, actually before I go further, let me just, one more piece of general nonsense. So you see, I wrote delta 0 and I wrote delta 1. And if you think about it, you can imagine what delta 2 is going to be, and delta 3, and so on and so forth. So the collection, delta I, define an element of the Hawkian homology of the chi category. That actually is very useful because one of the things applies to this applies, for example, once you've made the choice in order to obtain a pi grading, the second grading is compatible with multiplication. Weight is compatible with multiplication, i.e. W of x equals y W of x. So this by grading is an arbitrary extra structure. Here this is multiplication. Okay, so let me just give you some idea for what happens in this situation. So let's talk about T star x2. let me just tell you how we try to compute this by grading for the zero section. So remember, the zero section sits like this, corresponds to that. And now we have two that we want to compute this endomorphism. So first of all, delta 0 is necessarily 0 because, well, delta 0 lives in HF upper 1 of L with L. And that's the same thing as H upper 1 rest 2, which is 0. So we have no problem defining the invariant. It makes sense. The instruction bench. So we try to compute delta 1. So delta 1 is an endomorphism. It turns out that this endomorphism is degree preserving. Okay, so that's something that again follows by some dimension count, dimension formula. So it's an endomorphism on the zeroth cohomology, and it's an endomorphism on the second cohomology. So we have to compute two numbers. Great. So now, in order to compute these numbers, we have to understand the holomorphic disks which satisfy that condition. So the picture is like this. It's very hard to draw. So I have in a comprehensible way. So I have maybe some colors. So my Lagrangian sphere, it's like this. It starts at a point, and it becomes an equator, and it collapses back to a point. I don't know how to draw this in any better way. My divisor is D, is right here. Here's D. And then there's the epsilon, which I obtained by perturbing a little bit. Also over here. Okay, now I'm supposed to compute delta 1. I fix, sorry, to compute delta 1, I fix a point over here. I fix a, so let's try to compute delta 1 of the generator. So delta 1 from H0 plus 2 to H0 plus 2. Okay, so the way you do this is you fix a point on H0 plus 2, on S2, and count the number of configurations like this. So let's call it point X. So now you try to compute the number of configurations like that. But now you see exactly what they correspond to. Okay? So it's like I choose my point, it lives on one of these, there's a family of circles. There's no reason for me to pick the point here. I'm just going to pick the point inside. So it lives on one of these circles. So this is my X, for example. Okay? And if I try to count the number of disks with the right property of this line being aligned correctly, what I get is that this number is 0. We can make X avoid the image of the evaluation. So we have 0. That's one thing. So then we want to compute. So that means that the weight is 0 on each side. So then we want to compute this weight on delta 1, on H upper 2. So now, instead of fixing the point X, we want to consider all points X. Now consider all points. All possible. X2. And what you want to imagine is that you want to say, if you pick this point generically, how many disks do you see? sorry, no, that's not what I want to say. You look at all possible points, and then you want to basically pull back using the evaluation out from the space of disks, and then push forward using the evaluation out of the other. Go back here, push forward. But now what you see is that there's exactly 2 disks. There's this contribution from this disk and a contribution from this disk. Those are the only 2 disks that could possibly contribute to this when we let the point be completely generic. So there's 2 disks. And that implies that delta 1 is multiplication by 2. So once you know that delta, so that property, which is that the weight, so the weight on the element of degree 0 is 0. Or rather, so sorry, what we have gotten basically is that weight 4 has 2 weight equals homological grading. Now this condition is called purity. And this is actually something that you can extend to this computation. You can extend it to the relative Hilbert scheme, and you can show that in the relative Hilbert scheme there's a collection of Lagrangians. So in Yn there is a collection of Lagrangians which correspond to the crossless matchings. Let's write A n. Let's write H n for the category with these objects. For the Sakai category, it's existing exactly as the Lagrangians. And what you can compute is that this purity holds. So the weight lemma with respect to migrating defined using this basically this n of these divisors V. So there are these divisors that basically manage to define on AN and then just pass to the other scheme. HN is pure. So those who know something about quantum homology know that when you look at the arc algebra, the way Komanov migratings are defined, you have one of them is between degree 0 and n, and the other one is always in degree 0. That basically means my conventions differ from Komanov by like some affine transformation. So this is what I think the thing that I call weight is the homological gradient minus the Q gradient or something. The other way, something. Okay, so why did I go through this unmotivated explanation? Well, because one of the things that I tried to say last time, is that well, first of all, because now we have a second grading on synthetic quantum homology, even though I haven't explained to you at all why it would be invariant. But actually, that's not the main motivation. The main motivation is that this is needed in order to obtain the sort of formality results that we use to prove that the two theories are the same. So that's the last step. So first of all, what does it mean to be formal for an A-infinity algebra? So let's say C is, so first of all, what is an infinity algebra? I guess people don't know. So an A-infinity algebra and well, basically, it's like an algebra, so it's equipped with operations. At 1, this is a differential. At 2, this is a product. Product is not a assumed to be associative, but and 3 is basically homotopy that shows that M2 is associative homology. And you keep going. And 3 has the notion of associativity, which doesn't quite hold. It holds up to some M4, and so on and so forth. Great. So there's a particular class of A-infinity algebras that are useful to think about, which are minimal. So C is minimal if M1 is identical to 0. And there is a theorem that says, it goes back a long time, that every A-infinity algebra is equivalent to a minimal one. So now, I can at least tell you what it means to be formal. So C is formal if it is equivalent to a minimal algebra C. So this is script and this is without script. And this script guy has a property such that n 3 of C equals to 0 and 4 of C equals to 0 and so on. Okay, so we can say all higher products n. So this is like the DGA with no differential. Yes?
Is there a notion of equivalence on A-infinity algebras?
Very good question. I will tell you later. Why don't you ask me again? Because if I go through it, it will be too complicated. But let's say that it is not simply a linear map with the property that it intertwines operations. That's not what it is. There's some homotopical version of this. Okay. So that's what it means to be formal. Okay? The point is, Hovanov's art algebra is formal. Okay. Whatever Hovanov writes down, it has no differential, it has no higher products, it only has multiplication. On the other hand, this thing, which we would obtain, this category, script HN, which we would obtain by looking at the Lagrangians, has no reason a priori to be formal. For example, if you look at this category of the one-function torus, and you consider this Lagrangian and this Lagrangian, Killian Bruce, then this other name doesn't matter. So that this category consists of just these two objects is not formal. And this is very surprising, well, first sight, because the higher products in this kind of category, they all come from counting homomorphic disks. And you look at this picture, and you try to find some homomorphic disks, and you don't see any. Okay? And then the problem is that they're all hiding like here. They're at the constant. They're all hiding at the intersection point. When you try to define the category, you have to do some perturbations, and those perturbations produce some disks. You don't know whether there's a way of choosing the perturbations such that there are none, and they tell you that basically there is no way to do this. What we're going to say is that in the case of Hovanov homology, you get some spaces that kind of look like the analogs of these spaces, except replacing circles by spheres. Okay? And somehow we can prove not that there is a perturbation with no homomorphic disks, but rather that if count them, and you count them over the rationals, then there's an algebraic way of canceling them. So it's not explicit at all, but that's what formality says. Beyond the disks that contribute to N2, everything else cancels. So if you have a formal algebra, then you get a canonical element of functional cohomology as follows. So back to HH1. I shouldn't be erasing this. So given C, okay, which is just a graded algebra, i.e. from infinity algebra, in the way of this is obviously formal, because then the definition, like you can find something equivalent to this formal. It's already on the nose. We have the Euler vector field, which is what we call E of C. This is a map from, let's say, the ith part of C to the ith part of C, which takes x to I times. Let me just write degree of x, and of course, I'm just assuming that the degree of x is I. So this is an endomorphism of C. If you think about this endomorphism, notice that it has basically, because degree of x times y is equal to the degree, again, this is homological degree of x plus the degree of y. Because of this, E of C defines a class in H upper 1 of C coefficient in C. So this is subcoherent. If you try to think about what this functional cohomology group may not know what it is, but whatever it is defined by considering maps from C to C and higher powers, and this equation tells you that in fact you get a site. And now I can finally state the formality lemma that we use. So I learned this from Paul Seidel, although my understanding is that something like this is known to be Salish, but I also say. This is not too hard to believe. So assume that M1 C is equal to 0. This is really for simplicity. Okay. And then we're given some class E, okay, in HH upper 1 of C coefficients in C, such that two properties hold. Well, first of all, if you have a class in functional cohomology, one of the first things you can do is you can just see what element, it just defines for you an element of the algebra. So image E in C itself is equal to bench. And two, we introduce map from C to C, which is basically, so let's call this guy E of 0. This induced map is something we would call E of 1. The induced map agrees with the Euler vector. So the induced map takes every element to its degree times itself. These are two completely algebraic properties. The consequence is again something algebraic, which is that if we work over a field of characteristic 0, then C is formal. We work So all you need to do to prove the formality of some algebra, to prove the vanishing of higher products of some infinity algebra, is produce one element of its functional cohomology satisfying two equations.
Is it economic or is it?
It's actually economic, because I just showed you that in that case there is one. It's economic. But it's some sort of characterization of a formal infinity algebra. On the other hand, I just told you, actually it's what I'm erasing. So in our example, E is just this delta, this thing that was obtained by counting homomorphic disks with tasks of divisor and a nearby divisor, but with some extra condition. It satisfies all the conditions of the lemma. And that implies that the arc algebra, what I would call the symplectic arc algebra, so now let me have 30 seconds. So here's what would happen in the best of all possible worlds. You would take the symplectic algebra, you now know that it is formal. So you just check that as an algebra, it's the same as Hovanov's arc algebra. And then you would immediately conclude, no, actually one more thing. Then you would, and then these algebras come with breakgroup actions. So if you check that those breakgroup actions were the same, then you would conclude that symplectic Hovanov homology is the same as the usual Hovanov homology. Unfortunately, checking these signs, I can never decide whether we can prove it or not. I keep changing my mind. But what we can do is that starting with the symplectic arc algebra, the next step is to try to relate these algebras for different dimensions. So there'll be some bimodules over these arc algebras. And then there's the notion of formality for bimodules. It goes very much like the notion for algebras. There's a notion of higher multiplications. You would like for those to vanish. There is a criterion, kind of like this one, for formality of those bimodules. And you use the very same geometric construction, these deltas, together with some quills, to prove that the bimodules that show up in symplectic homology are themselves formal. Once you have that, you get a hypercube of resolutions with no diagonal elements that compute symplectic homology. So all that's left is comparing that hypercube of resolution to the one for symplectic homology. For ordinary homology, this is something that was probably first done by Kappas and Hamilton when they proved that Hovanov homology can be computed from coherent sheaves. So we basically just look at what they did and adapt it to the symplectic setting, and then check that the two algebras are the same over Q. That's it.
Comments or questions? Okay.
So do you know if the cube gradient you get is the same one that Trippering sort of found using the cradle construction?
I have no idea. I have no idea. Honestly, I don't know what he did, so I don't know. Do you have?
I actually have no idea why I do know what he did. That's a good question. I haven't thought about it. Anyone else want to do more? Great, let's have coffee. Thanks for having it again. We're resuming half an hour.